Good evening, everyone, and welcome to the Droning Professor. Tonight, we're going to learn about Aristarchus. So, as you make yourselves comfortable, please take a moment to let us know where you're listening from and feel free to subscribe. Now, as always, take a moment for some deep breaths, letting your mind and body relax for a good night of sleep. Tonight, we're going to talk about a man who was so right he was wrong for 1800 years. A man who looked up at the night sky and saw what no one else could see. A man who said, "You know what? I think we're spinning around the sun." And everyone else said, "That's adorable. Now sit down." His name was Aristarchus of Samos, and he might just be the most frustratingly vindicated person in the history of science. Now, before we dive in, let me set the stage. We're talking about ancient Greece, not the Greece of Socrates and Plato. That was earlier. Not the Greece of Alexander the Great conquering everything in sight. That was a bit earlier too. We're talking about the Greece of around 310 before Common Era to 230 before Common Era. This is the Hellenistic period, baby. Alexander has already died. His empire has fractured into pieces, and one of those pieces, Egypt under the Ptolemies, has become the intellectual center of the entire Mediterranean world. The Library of Alexandria is filling up with scrolls. Mathematicians are doing mathematics. Astronomers are doing astronomy. And somewhere, on a little island called Samos, a boy is born who will grow up to tell everyone they've got the whole universe backwards. Samos, by the way, is this beautiful island in the eastern Aegean Sea, close to what's now Turkey. It's the same island that gave us Pythagoras a few centuries earlier, you know, the triangle guy. So Samos had a reputation for producing people who looked at the world and said, "But what if we measured it?" Aristarchus was born into this tradition of measurement, of trying to figure out what's actually happening up there in the cosmos, not just making up stories about gods pulling the sun across the sky in a chariot. Now, what do we know about Aristarchus the person? Honestly, not much. This is the annoying thing about ancient history, especially ancient science history. We don't have his autobiography. We don't have letters where he complains about his colleagues. We don't even have most of his original writings. What we have are references to him by other people, little mentions here and there, like astronomical footnotes. We know he studied in Alexandria, probably under a philosopher named Strato of Lampsacus, who was head of the Lyceum, which was Aristotle's old school. We know he was good at mathematics. We know he was interested in astronomy. And we know that at some point he published ideas that were so radical, so completely bonkers to his contemporaries, that he was accused of impiety. That's ancient Greek for "you're messing with our religion, buddy." But before we get to the crazy revolutionary stuff, let's talk about the work of Aristarchus that actually survived, the work that made everyone say, "Okay, this guy's brilliant," right before they ignored his best idea for 2 millennia. I'm talking about his treatise on the sizes and distances of the sun and moon. This is the only work of Aristarchus that we still have in complete form, and let me tell you, it's a masterpiece of ancient geometry. Not because it gets the right answers, it doesn't, but because it shows a mind that understood how to use observation, mathematics, and logical reasoning to figure out things that seem completely impossible to figure out. Picture this. You're standing on Earth, you can see the moon, you can see the Sunday. They both look like little circles in the sky. How, in the name of Zeus, are you supposed to figure out how big they are and how far away they are? You can't exactly fly up there with a measuring tape. You can't even be sure they're not just like little lights painted on a dome. But Aristarchus said, "I can figure this out." And he did. Sort of. Here's the key insight. During a half moon, the one where exactly half the moon is lit up, the moon is seeing the sun at a right angle from our perspective. Imagine you're the moon for a second. The sun is shining on you from one direction. Earth is looking at you from another direction. When Earth sees you as exactly half lit, the angle between the sun to moon line and the moon to Earth line is 90 degrees. That's a right angle. That's a right triangle in the sky. And if you've got a right triangle, you can use geometry. The ancient Greeks loved them some right triangles. Aristarchus measured the angle between the moon and the sun at the exact moment of half moon. He said it was 87 degrees. Now, we know today he was wrong. It's actually 89.85 degrees, which is much closer to 90 degrees. But his method was sound. With that angle, using some trigonometry, well, they didn't call it trigonometry yet, but using geometric reasoning about triangles, Aristarchus calculated that the sun was between 18 and 20 times farther away from Earth than the moon was. The real answer is about 390 times farther. But again, we're not here to mock his precision. We're here to appreciate that he figured out how to even approach this question. And then he went further. During a lunar eclipse, Earth's shadow falls on the moon. By carefully observing how long it takes the moon to pass through Earth's shadow, and how big the shadow is compared to the moon, Aristarchus calculated that Earth was bigger than the moon. Specifically, he figured the diameter of Earth was about 3 times the diameter of the moon. The real ratio is about 3.7, so he was remarkably close on this one. He also calculated, using similar geometric logic, that the sun was way bigger than Earth. He said about 7 times bigger in diameter. The actual number is about 109 times, but again, the method was brilliant, and the conclusion was correct. The sun is enormous compared to us. Think about what this means. Aristarchus has just demonstrated, using mathematics and observation, that the sun is gigantic. It's not a little light in the sky. It's a massive object, much bigger than the entire Earth. And here's where his brain does something extraordinary. He thinks, if the sun is so much bigger than Earth, why would it orbit Earth? Wouldn't it make more sense for the smaller thing to orbit the bigger thing? This is where we get to the heliocentric model. Helios, the Sunday-centric, center. Sun at the center. Aristarchus proposed that the Earth and the other planets orbit the sun, and that Earth spins on its axis once a day, which is why we see the stars appearing to move across the sky. He said the stars are incredibly far away, so far that we can't detect any change in their positions as Earth moves around the Sunday. And with that, Aristarchus of Samos, around 260 before Common Era, invented the model of the solar system that we now know is correct. And everyone said, "That's nice, Aristarchus. Now go sit in the corner with the other people who have weird ideas." Why? Why did nobody listen to him? Well, let's be fair to the ancient world. Aristarchus's idea had some problems. From their perspective, first, common sense. If Earth is spinning, why don't we feel it? Why doesn't everything fly off into space? Why don't the clouds get left behind? If you're standing on a moving platform, you feel it move. Earth doesn't feel like it's moving. Second, if Earth is orbiting the sun, the stars should shift position slightly when viewed from different points in Earth's orbit. This is called stellar parallax, and the ancient astronomers looked for it and didn't see it. Aristarchus said the stars are just really, really far away, so the parallax is too small to detect. Which was correct, but it's also convenient, isn't it? My theory predicts something you can't see, because it's too small to see is not the most compelling argument. Third, and this is big, physics. Aristotle had explained how the universe worked, and in Aristotle's physics, heavy things naturally move toward the center of the universe. Earth is heavy. Earth is made of heavy stuff like rock and water, so Earth should be at the center. The sun and moon and stars are made of some kind of perfect celestial stuff that naturally moves in circles, so they should orbit Earth. If you accept Aristotelian physics, and everyone did, then a heliocentric universe doesn't make physical sense. You'd need a completely different understanding of motion and gravity to make it work. And that wouldn't come along for another 1800 years or so, when a guy named Isaac Newton showed up with his laws of motion and universal gravitation. Fourth, religious and philosophical objections. The idea that Earth was at the center of the universe felt right, cosmically speaking. Humans are important. We're the focus of creation. The gods care about us. If we're just on one planet circling a sun that's circling around in an unimportant part of space, that feels, I don't know, lonely, diminishing. Some ancient writers accused Aristarchus of impiety for displacing Earth from the center of the cosmos. Though, to be fair, we're not entirely sure how serious these accusations were, or if anything actually happened to him. He wasn't executed or anything. He probably just got side-eyed at symposia. So, instead, the ancient world went with the geocentric model. Earth at the center, everything else orbiting around it. This got refined over the centuries into incredibly sophisticated models, especially by Claudius Ptolemy around 150 of the Common Era. Ptolemy's model was geocentric, but it was brilliant in its complexity. It had epicycles, little circles on top of bigger circles, to explain why planets sometimes appear to move backwards in the sky. It could predict planetary positions with impressive accuracy. It worked. And because it worked, it lasted all through the Roman Empire, through the fall of Rome, through the Middle Ages in Europe, and the Islamic Golden Age. Ptolemy's geocentric universe was the universe. Aristarchus, meanwhile, became a footnote. People knew about him. Other ancient writers mentioned his heliocentric idea. Archimedes, the famous mathematician, wrote about it in a work called The Sand Reckoner, where he mentioned that Aristarchus proposed a universe where Earth orbits the Sun and the stars are incredibly distant. Plutarch mentioned it. A few other writers here and there dropped Aristarchus's name when discussing cosmological models. But always in a kind of here's a weird idea someone once had way. It wasn't taken seriously. It was the astronomical equivalent of some guy on the internet said, interesting, but not, correct. Except it was correct. It was absolutely, fundamentally correct. Fast forward to the 16th century of the Common Era. A Polish mathematician and astronomer named Nicolaus Copernicus is working on a book. He's troubled by the complexity of Ptolemy's system. All these epicycles, all these adjustments. It works, but it's ugly. Copernicus thinks, what if we put the sun at the center? And he develops a heliocentric model. Now, Copernicus probably knew about Aristarchus. In early drafts of his manuscript, he actually mentions Aristarchus and the ancient heliocentric idea. But in the final published version, which came out in 1543, right as Copernicus was dying, the reference to Aristarchus is gone. Maybe he removed it himself. Maybe an editor did. We don't know. But the result is that Copernicus gets credit for the heliocentric model in the popular imagination, and Aristarchus remains obscure. To be fair, Copernicus's model was more developed. He provided detailed mathematical descriptions of planetary orbits. He worked out the order of the planets. He made predictions. Aristarchus's heliocentric proposal, from what we can tell, was more of a conceptual claim. The sun should be at the center. He didn't have a full mathematical model to compete with Ptolemy. So Copernicus definitely deserves credit for doing the hard mathematical work. But Aristarchus deserves credit for having the insight first, for looking at the evidence and reaching the correct conclusion about the structure of the solar system 1700 years earlier. And then, of course, things got spicy. The Catholic Church was not thrilled with heliocentrism. It contradicted certain passages of Scripture that talked about the sun moving across the sky and Earth being immovable. In 1616, heliocentrism was declared foolish and absurd in philosophy and formally heretical. Galileo Galilei, who had been enthusiastically promoting the Copernican model and making observations with his fancy new telescope that supported it, got hauled before the Inquisition and forced to recant. He spent the last years of his life under house arrest. All because he said Earth moves around the sun. an idea that Aristarchus had proposed nearly 2,000 years earlier without, as far as we know, getting inquisitioned. Eventually, of course, the evidence became overwhelming. Johannes Kepler figured out that planetary orbits are ellipses, not circles, which made the math work way better. Isaac Newton explained the physics of why planets orbit the Sun, providing the gravitational framework that the ancient world lacked. In the 18th and 19th centuries, astronomers finally detected stellar parallax, the tiny shift in star positions that Aristarchus predicted, confirming that Earth does indeed orbit the Sun, and that the stars are extremely distant. The heliocentric model became the scientific consensus. Earth was demoted from the center of the universe to the third planet from the Sun in an average solar system, in an ordinary galaxy in a vast cosmos. Aristarchus was vindicated, though he'd been dead for about 2,000 years and probably wasn't in a position to enjoy it. Let's go back to on the sizes and distances of the Sun and Moon for a moment, because there's something beautiful about this work that I want to highlight. Aristarchus was trying to measure the cosmos using nothing but his eyes, some careful timing, and geometry. No telescopes, no spacecraft, no computers. Just looking up at the sky and thinking really hard. And the method he used, comparing angular sizes and using geometric principles to infer physical sizes and distances, is fundamentally sound. It's the same kind of reasoning astronomers use today, just with better instruments and more sophisticated mathematics. For example, Aristarchus knew that during a solar eclipse, the moon exactly covers the sunday. They have the same angular size in the sky. But he'd calculated that the sun is much farther away than the moon. If two objects have the same angular size but one is much farther away, the farther one must be physically much larger. Imagine holding a coin at arm's length. It might cover the moon in your vision. But the moon isn't coin-sized, it's just far away. Same principle. Aristarchus understood this. But is my cast just inside? He understood that the cosmos was vast, that objects could be much larger and farther away than they appeared. He also understood the power of mathematical reasoning. His treatise is structured as a series of propositions and proofs, very much in the style of Euclidean geometry. If we assume this, and we observe that, then it logically follows that this other thing must be true. This is the scientific method avant la lettre. Hypothesis, observation, logical deduction, conclusion. It's rigorous. It's systematic. And it's why, even though his numerical results were off, his approach was exemplary. There's a hypothesis floating around among some historians of science that Aristarchus's measurements were deliberately designed to give him the results he wanted. That he fudged the numbers to make the sun come out much larger than Earth, which would then justify his heliocentric model. Maybe he measured that angle at half moon and got something more like 89 degrees, but wrote down 87 because it gave him a sun-to-moon distance ratio that made his argument stronger. We'll never know if this is true. It's hard to assign motivations to someone from 2,300 years ago based on a single surviving text. But if he did fudge the numbers, honestly, I kind of respect it. He had the right idea. He knew the sun should be at the center. He was trying to build a mathematical argument to convince people. If he had to nudge the data a bit to make the argument work, well, that's unfortunate from a scientific ethics standpoint, but very human. More likely, though, his measurements were just genuinely difficult to make accurately. Try it yourself sometime. Go outside at half moon and try to measure the angle between the moon and the sun with any precision. The sun is incredibly bright. You can't look directly at it. The moon is often visible during the day at half moon, but it's faint. Your measuring tools are ancient Greek technology, so maybe a staff and some sighting devices, no precision instruments. You're estimating angles by eye. An error of a couple degrees is completely understandable. And a couple degrees when you're working with angles close to 90 degrees throws off your calculations dramatically. Aristarchus did the best he could with what he had. Let's talk about the stars for a minute. Aristarchus said the stars are incredibly far away, so far that Earth's orbit around the Sun is like a point compared to the distance to the stars. This was a necessary part of his model to explain why we don't see stellar parallax. But think about what this implies. He's saying the universe is vastly, almost incomprehensibly large. The stars, which look like little pinpricks of light, are actually distant suns, maybe like our sun, just incredibly far away. Now, we don't know if Aristarchus explicitly said the stars are other suns, but the implication is there. And if the stars are other suns, maybe they have their own planets. Maybe there are other worlds. This is speculation, but it's the kind of speculation that becomes possible once you accept the heliocentric model and the vastness of space. The ancient world had a cozy cosmos. The sphere of the stars wasn't that far away, maybe just beyond Saturn. You could kind of mentally encompass it. Aristarchus's cosmos is not cozy. It's vast, cold, and largely empty. Earth is a tiny speck. The sun is much bigger, but still a tiny speck compared to the distance to the stars. This is a modern-feeling universe, a universe that wouldn't feel out of place in a Carl Sagan documentary, and Aristarchus intuited it 2,000 years before Sagan. Now, why didn't Aristarchus's ideas catch on? We've talked about the scientific and philosophical objections, but there's also just the inertia of established ideas. Aristotle was the great philosopher. His ideas dominated intellectual life for centuries. Challenging Aristotle wasn't just challenging a scientific theory. It was challenging an entire worldview, a system of thought that covered physics, metaphysics, ethics, politics, everything. Aristarchus was one guy with a weird idea about the cosmos. Aristotle was Aristotle. It's not surprising that Aristotle won. There's also the fact that astronomy, in the ancient world, was closely tied to astrology. People cared about the positions of the planets because they believed those positions influenced human affairs. Ptolemy's geocentric model could predict planetary positions accurately enough for astrological purposes. Aristarchus's heliocentric model, without the detailed mathematical framework, couldn't. So from a practical standpoint, why switch? The geocentric model worked for what people needed it for. But let's give some credit to the people who kept Aristarchus's memory alive. Archimedes, in The Sand Reckoner, doesn't just mention Aristarchus in passing. He takes the heliocentric model seriously enough to use it as the basis for a thought experiment about the size of the universe. Archimedes is trying to figure out how many grains of sand it would take to fill the entire cosmos, and he uses Aristarchus's model of a huge universe with distant stars as his starting point. So even though Archimedes doesn't endorse heliocentrism, he treats it as a legitimate cosmological idea worth engaging with. Plutarch, writing in the 1st and 2nd centuries of the Common Era, discusses Aristarchus in his work On the Face, in the Orb of the Moon. He mentions that Aristarchus was accused of impiety for putting Earth in motion and displacing it from the center of the universe. Plutarch also preserves some details of Aristarchus's arguments, which is valuable since Aristarchus's own writings on heliocentrism are lost. So we have Plutarch to thank for some of what we know about Aristarchus's ideas. And then there are the astronomers of the Islamic Golden Age. From roughly the 8th to the 14th centuries of the Common Era, while Europe was in the Middle Ages, the Islamic world was a powerhouse of scientific and mathematical advancement. Arabic-speaking scholars translated Greek texts, including works of astronomy, and built on them. They knew about Aristarchus. They debated cosmological models. Some of them proposed modifications to Ptolemy's system that edged toward heliocentrism, though none quite took the full step that Aristarchus had. But they kept the conversation alive, and their work would eventually be transmitted to Europe, where it influenced the Renaissance astronomers like Copernicus. So Aristarchus's legacy, even if he was ignored or dismissed, persisted. His ideas were never completely forgotten. They were always there, in the background, a dissenting voice in the geocentric consensus. And when the time was right, when the scientific revolution began and people started questioning Aristotelian physics and Ptolemaic astronomy, Aristarchus was waiting, like a time capsule from the ancient world, saying, "I told you so." Let's talk about the sheer audacity of Aristarchus's claim. Imagine you're living in the ancient world. The evidence of your senses tells you that you're standing still, and the sun is moving across the sky. Everyone you've ever met agrees with this. The greatest philosophers and scientists of your civilization have built elaborate theories around this. And you come along and say, actually, we're the ones moving. Earth is spinning like a top, and we're hurtling through space around the sun at incredible speeds. And we don't feel any of it because everything is moving together. People would think you're insane, or high, or both. But Aristarchus said it. And he backed it up with reasoning. Look, the sun is huge. Earth is tiny compared to the Sunday. It makes more sense for the tiny thing to orbit the huge thing. This is a persuasive argument, but it requires a kind of conceptual flexibility that's not easy to come by. It requires you to distrust your own senses and trust mathematical reasoning instead. That's a big ask. And the spinning Earth thing. Aristarchus said Earth rotates on its axis once a day, which is why the stars appear to move. This explains the daily motion of the heavens without requiring the entire cosmos to rotate around Earth every 24 hours. But again, if Earth is spinning, why don't we feel it? Why doesn't the air whip past us at incredible speeds? The answer, which Newton would eventually provide, is that the atmosphere is moving with Earth, and we're moving with Earth, and there's no friction against some stationary background to slow us down. But in the ancient world, this was not intuitive. Here's an analogy that sometimes helps. Imagine you're in a car driving smoothly down a highway at 60 miles per hour. If you toss a ball straight up in the air inside the car, does it fly backward and smack you in the face? No. It goes straight up and comes straight down, even though the car and you and the ball are all moving forward at 60 miles per hour. That's because you, the ball, and the car are all moving together. Earth is like that car, but much bigger and moving much faster. We're all moving together, so we don't feel it. But the ancient Greeks didn't have cars. They had ox carts, which don't exactly provide a smooth, constant velocity reference frame. So the intuition wasn't there. Aristarchus was asking people to accept a radically counterintuitive model based on mathematical reasoning about the sizes and distances of celestial objects. No wonder they didn't listen. What's remarkable is that he had the insight in the first place. Now, we've been talking about Aristarchus as an astronomer, but he was also part of a broader intellectual milieu in Alexandria. The Hellenistic period was a golden age of Greek science. Euclid was writing his Elements, the textbook of geometry that would be used for over 2,000 years. Archimedes was inventing calculus before calculus was a thing, calculating areas and volumes of complex shapes. Eratosthenes was measuring the circumference of Earth by comparing the angles of the sun's rays in different cities, coming up with a result that was remarkably accurate. Apollonius was studying conic sections, ellipses, parabolas, hyperbolas. These shapes would turn out to be crucial for understanding planetary orbits, though nobody knew that at the time. This was a culture that valued mathematics, observation, and logical reasoning. It was a culture that believed the universe could be understood, that it followed rational principles, and that human minds could figure out those principles. Aristarchus was a product of this culture, and his work reflects its values. He didn't just say, "I think the sun is at the center." He said, "Here's how we can use observations and geometry to figure out the sizes and distances of celestial objects, and here's what that implies about the structure of the cosmos." That's the scientific method. That's Enlightenment thinking, emerging in the 3rd century before Common Era, and then it got lost. The Roman Empire was more interested in engineering and administration than in theoretical science. The Library of Alexandria, that great repository of knowledge, was damaged and diminished over the centuries through neglect, fire, and conflict. Texts were lost. The chain of transmission was broken. By the time of the fall of Rome in the 5th century of the Common Era, much of Greek science was unavailable in Western Europe. It survived in the Byzantine Empire and was translated into Arabic during the Islamic Golden Age, but Europe largely forgot it. The Renaissance involved, in part, rediscovering and retranslating Greek texts. Copernicus, Kepler, and Galileo were building on a foundation laid by people like Aristarchus, but they had to reconstruct much of it from fragmentary sources. What would have happened if Aristarchus's heliocentric model had been accepted in the ancient world? It's one of those great historical counterfactuals. Would it have accelerated scientific progress? Would we have reached the space age in the Middle Ages? Probably not. The problem wasn't just the model of the solar system. The problem was the entire framework of physics. Aristotelian physics couldn't explain a heliocentric universe. You needed Newtonian physics, and to get to Newton, you needed Galileo's experiments on motion, and Kepler's laws of planetary motion, and Descartes' coordinate geometry and calculus. You needed a whole scientific revolution, a complete overhaul of how people thought about the natural world. Aristarchus was ahead of his time, but he was really ahead of his time. He had one crucial insight, but building a new physics around that insight would take centuries of work by dozens of brilliant people. Still, it's fun to imagine an alternate timeline where Aristarchus convinced everyone, where on the heliocentric universe became the standard cosmology, where Ptolemy developed elaborate mathematical models of elliptical orbits around the Sun instead of epicycles around Earth, where the medieval church taught that Earth circles the Sun just like it taught that God created the heavens and the earth, where Galileo didn't get in trouble because everyone already knew Earth moves. It's a nice fantasy, but it's not what happened. What happened is that Aristarchus wrote down his ideas, a few people mentioned them, and then everyone went on believing in a geocentric universe for another 1800 years. And you know what? That's okay. Science doesn't always progress smoothly. Sometimes the right ideas have to wait for the right context, the right evidence, the right framework to make sense. Aristarchus planted a seed, and Copernicus reaped the harvest much later. That's how intellectual history works sometimes. Let's talk about the moon for a bit. Aristarchus did a lot of work on the moon. His treatise calculates its size and distance. He understood lunar phases, why the moon looks different at different times of the month. He understood lunar eclipses, why the moon sometimes passes through Earth's shadow. The moon was the easiest celestial object to study because it's close and it changes. The sun is too bright to look at. The stars are too far away to show any detail. But the moon, you can watch the moon. You can see its features, its light and dark patches. You can track its motion across the sky night by night. Aristarchus measured the angular size of the moon during a lunar eclipse and compared it to the size of Earth's shadow. He figured out that Earth's shadow, at the distance of the moon, was about twice the diameter of the moon. From this, using some geometric reasoning, he calculated the size of the moon relative to Earth. He also calculated the distance to the moon based on its angular size and estimated diameter. His methods were sophisticated and, given the limitations of his tools, impressively accurate. The moon plays a crucial role in the history of astronomy because it's the one celestial object, other than the sun, that shows clear, observable changes. It waxes and waxes, it eclipses, it has features you can see with the naked eye. For ancient astronomers, the moon was proof that the heavens weren't some unchanging, perfect realm. They had dynamics, they had geometry, they had phenomena that could be studied and explained. Aristarchus was part of that tradition of careful observation and mathematical explanation of lunar phenomena. There's a poetic irony to Aristarchus studying the moon so carefully from Earth, given that we now know the moon orbits Earth. He was right about Earth orbiting the sun, but the moon really does orbit Earth. So, in a heliocentric model, We're still the center of something, just not the center of everything. Earth and Moon together orbit the Sun, a binary planet system, though we don't usually call it that. Aristarchus understood the Earth-Moon system pretty well, even if his distances were off. He knew the Moon was closer than the Sunday. He knew the Moon was smaller than Earth. He knew the system had geometry and proportions that could be worked out mathematically. That's a huge achievement. Now, let's address the elephant in the room, or the geocentrist in the room. Were the ancient geocentrists stupid for not believing Aristarchus? No, absolutely not. They had good reasons, given what they knew and the tools they had, to believe Earth was at the center. The geocentric model explained the observations. It was consistent with the physics they understood. It was intuitive. It fit with their philosophical and religious worldview. And crucially, the heliocentric model, as Aristarchus proposed it, didn't obviously work better. It didn't make better predictions. It didn't explain more phenomena. It was just a different way of arranging the cosmos, and a less intuitive one at that. The lesson here isn't the ancients were dumb. The lesson is science is hard, and the right answer isn't always obvious. It took incredible genius for Aristarchus to come up with the heliocentric model. And it took further incredible genius, centuries later, for Copernicus, Kepler, Galileo, and Newton to develop the heliocentric model into a full scientific theory that could replace geocentrism. We shouldn't mock the people who believed Earth was at the center. We should marvel at the people who figured out it wasn't. Let's also appreciate the fact that we have any of this at all. The survival of ancient texts is a miracle of chance. On the sizes and distances of the Sun and Moon survived because someone in the Byzantine Empire copied it, and then someone else copied that copy, and eventually it was printed in the Renaissance, and we still have it today. But Aristarchus's other works? Gone. His treatise on heliocentrism? Gone. We know about it only because other people mentioned it. How many other brilliant ideas from the ancient world are completely lost because the texts didn't survive? How many other Aristarchuses are there whose names we don't even know? It's sobering to think about. This is why we cite our sources, people. This is why we preserve texts. This is why libraries and archives matter. Knowledge is fragile. It can be lost. The fact that we know about Aristarchus at all is thanks to scribes and librarians and scholars who valued old books and kept them safe. So, next time you're in a library, maybe give a little mental thank you to the librarians. They're the reason we have history. Okay, we're about 60 minutes in. Let's talk about legacy and influence, and then we'll wrap up. Aristarchus's direct influence on the scientific revolution is debatable. Copernicus knew about him, at least early on. Did Aristarchus's ancient precedent embolden Copernicus to propose heliocentrism? Maybe. It's hard to say. But Aristarchus certainly provided historical support for the idea. He was proof that heliocentrism wasn't some crazy new theory. It was an old idea being revived, and ancient ideas had a lot of prestige in the Renaissance. If an ancient Greek proposed it, it couldn't be that radical, right? Aristarchus is also a symbol, a figure we can point to and say, look, even in the ancient world, someone figured this out. He's a reminder that brilliance and insight can occur in any era, that the march of progress isn't linear, and that sometimes the right ideas have to wait for the right moment. He's a cautionary tale about how ideas can be ignored or dismissed if they don't fit the prevailing paradigm. And he's an inspiration for anyone who's ever had an idea that everyone else thought was crazy. Maybe you're right. Maybe you're the next Aristarchus. Or maybe you're wrong and you should listen to the experts. It's hard to tell in the moment. In modern astronomy, Aristarchus has a crater on the Moon named after him. It's a young, bright crater with a spectacular ray system that extends for hundreds of kilometers across the lunar surface. It's one of the most prominent features on the Moon, visible from Earth with binoculars or even sharp naked eyes under the right conditions. So Aristarchus, who studied the Moon from Earth, now has a piece of the moon named after him. There's a pleasing symmetry to that. He also has a small planet, asteroid, named after him, 1538 Aristarchus. It's a main belt asteroid discovered in 1936. It's about 10 kilometers across and orbits the Sun between Mars and Jupiter. So Aristarchus, who proposed that Earth orbits the Sun, now has a space rock orbiting the Sun in his name. The universe has a sense of humor. What can we learn from Aristarchus today? First, that observation and measurement are the foundations of science. Aristarchus didn't just speculate. He measured. He calculated. He used the best tools and methods available to him to figure out what was actually happening. Second, that mathematics is a powerful tool for understanding the universe. Geometry allowed Aristarchus to infer things he couldn't directly observe: the sizes of the sun and moon, their distances, the scale of the cosmos. Third, that being right isn't enough. You also need evidence, a framework that makes sense of the evidence, and the ability to convince other people. Aristarchus was right, but he couldn't prove it in a way that overcame the objections of his time. Fourth, that progress isn't inevitable. Good ideas can be lost or ignored. It takes work to preserve and transmit knowledge across generations. But here's the thing that really gets me about Aristarchus. He was one person, on one small island, in one brief moment of human history, and he looked up at the sky and figured out something profound about reality. He didn't have textbooks. He didn't have Wikipedia. He didn't have centuries of accumulated scientific knowledge to draw on. He had his eyes, his brain, some geometric principles, and the courage to think differently from everyone else. And he got it right. That's the power of human reason. That's what science is all about. Observation, reasoning, following the evidence wherever it leads, even if it leads somewhere uncomfortable or counterintuitive. Aristarchus embodied that spirit. He's a hero of science, even though most people have never heard of him. He's proof that one person, thinking carefully and clearly, can see truths that are hidden from everyone else. And yet, he was also wrong about a lot of things. His measurements were off. He didn't have a complete model of orbital mechanics. He didn't understand gravity. He was working with incomplete information and imperfect tools, and that's okay too. That's how science works. You make your best guess based on the evidence you have. You put forward a hypothesis. Other people test it, refine it, improve it. Over time, over generations, the picture becomes clearer. Aristarchus started that process for heliocentrism. Copernicus continued it. Kepler refined it. Newton explained it. And today, we have spacecraft exploring the solar system that Aristarchus intuited 2,300 years ago. Think about what Aristarchus would make of the modern world. We've sent probes to every planet in the solar system. We've landed on Mars, Venus, the Moon, an asteroid, a comet. We've sent spacecraft beyond the edge of the solar system into interstellar space. We have telescopes that can see galaxies billions of light years away. We know the universe is expanding. We know it began in a Big Bang about 13.8 billion years ago. We know that the Sun is one star among hundreds of billions in our galaxy, and our galaxy is one among trillions in the observable universe. We've discovered thousands of planets orbiting other stars. We've detected gravitational waves, ripples in space-time itself. Aristarchus said the stars are really far away. He had no idea. The nearest star to our Sun, Proxima Centauri, is about 4.2 light-years away. That means light, traveling at about 300,000 kilometers per second, takes 4.2 years to reach us from Proxima Centauri. In more human terms, it's about 40 trillion kilometers. If you got in a car and drove at highway speeds, it would take you about 40 million years to get there, and that's the nearest star. The galaxy is about 100,000 light-years across. The observable universe is about 93 billion light-years across. Aristarchus said the stars are distant to explain the lack of parallax. He was right, but he couldn't have imagined how distant. And here's the kicker. We did eventually detect stellar parallax. In the 1830s, astronomers using much better telescopes than anything available to Aristarchus measured the tiny shifts in star positions as Earth orbits the Sunday. The parallax angles are tiny, measured in fractions of a second of arc. A second of arc is 1/3600th of a degree. The parallax of the nearest stars is less than 1 second of arc. No wonder the ancient Greeks couldn't detect it. They were looking for something that requires precision instruments to see. But Aristarchus predicted it would be there, and he was right. So here we are, in the 21st century, with all our telescopes and spacecraft and computers, and we've confirmed everything Aristarchus said. Earth orbits the Sunday. The Sun is much larger than Earth. The stars are incredibly distant. We've measured it all. We've photographed it. We've sent robots to explore it. And somewhere, across the vast gulf of time, Aristarchus is vindicated. I like to imagine Aristarchus's ghost, wandering through the centuries, watching as his ideas were ignored, then rediscovered, then confirmed, then expanded into an understanding of the cosmos that even he never dreamed of. I imagine him watching Galileo point his telescope at Jupiter and discover moons orbiting Jupiter, little solar systems within the solar system, watching Newton write down the law of universal gravitation, explaining why planets orbit the Sunday, watching Hubble discover that the universe is full of galaxies, each with hundreds of billions of stars, watching Armstrong step onto the moon, that object Aristarchus studied so carefully, watching the Voyager spacecraft leave the solar system and enter interstellar space, carrying a message to anyone who might find them. We are here. We figured out where we are. We're exploring. Aristarchus would love it. He'd probably have a million questions. And he'd definitely say, "I told you so." Of course, we've also learned that Aristarchus's heliocentric model, while correct for the solar system, doesn't extend to the universe as a whole. The Sun isn't at the center of the galaxy. The galaxy isn't at the center of the universe. In fact, the universe doesn't have a center, or if it does, we can't identify it. The universe is homogeneous and isotropic on large scales, meaning it looks basically the same in all directions. There's no privileged position. Earth isn't at the center, but neither is the Sun or the Milky Way or anything else. We're just somewhere in the cosmos, which is vast and mostly empty and governed by physical laws that we're still working to understand. But Aristarchus got us started on that journey. He was the first, as far as we know, to seriously propose that Earth isn't the center of everything. He opened the door to a cosmos that doesn't revolve around us, literally or figuratively, and that's a profound shift in perspective. It's humbling. It's awe-inspiring. It's the beginning of the modern scientific worldview. So what's the takeaway from all this? What's the lesson of Aristarchus? Maybe it's that truth isn't always obvious. Maybe it's that the right answer might be the one that feels wrong. Maybe it's that we should be willing to question our assumptions, to follow the evidence even when it leads somewhere uncomfortable. Maybe it's that brilliance can appear anywhere, anytime, and we should pay attention when someone says something that challenges the consensus, because maybe, just maybe, they're seeing something the rest of us have missed. Or maybe the lesson is simpler. Look up. Look at the night sky. Think about what you're seeing. The moon, the planets, the stars. They're not just pretty lights. They're objects, physical things with sizes and distances and motions. They're part of a vast cosmos that follows rules we can figure out. Aristarchus looked up and saw not just lights in the sky, but a geometric puzzle he could solve. And he solved it brilliantly, even if nobody believed him. We're all standing on Earth, just like Aristarchus was. We're all spinning through space at incredible speeds, orbiting the Sun, which is orbiting the center of the galaxy, which is moving through the universe. We don't feel it. It's invisible to our senses. But it's real. Mathematics and observation have revealed it. Science has revealed it. And it all started with people like Aristarchus, people who looked at the world and asked, what's actually happening here? Aristarchus of Samos, born around 310 before Common Era, died around 230 before Common Era, astronomer, mathematician, and the man who first proposed that Earth orbits the Sunday. He was right. It took the world 1800 years to realize it, but he was right. He measured the cosmos with nothing but geometry and determination. He challenged the greatest minds of his age. He lost that argument in his lifetime, but he won it in history. He's a testament to the power of human reason, the importance of intellectual courage, and the long, slow, frustrating, beautiful process of figuring out how the universe works. So the next time you're outside at night, look up at the stars. Think about Aristarchus. Think about how far we've come since he stood on Samos and calculated the size of the Sunday. Think about how much we've learned, how much we've explored, how much we've discovered, and think about how much we still don't know. The cosmos is vast. It's full of mysteries. And somewhere out there, maybe on another planet orbiting another star in another galaxy, someone else is looking up at their night sky, doing their own calculations, asking their own questions, and maybe, just maybe, figuring out something that no one else has ever realized. That's the legacy of Aristarchus. Not just the heliocentric model, though that's important, but the idea that we can understand the universe. That observation and reason can reveal truth. That the cosmos is knowable. That we, tiny creatures on a tiny planet, can look up at the infinite expanse and make sense of it. Aristarchus was right about the Sunday. He was right about Earth's place in the solar system. He was right about the vast distances to the stars. He saw the future of astronomy 2,000 years before it arrived. He deserves to be remembered. He deserves to be celebrated. He deserves to have his name known alongside Copernicus and Galileo and Newton, because he was there first. He lit the spark that would eventually become the scientific revolution. Good night. And in case you've enjoyed our evening talk so much and still might be awake, here is another educational video for you.